Here's where we left off on the last slide. We were looking at this function to find out if our critical point of e negative 2 was a max, a min, or neither. So I'm doing the first derivative test. I'm looking on both sides of the critical point. Because e is about 2.7, I'm going to test at 2 and at 3. So f of 2, I have it somewhere, equals 2 over e, natural log of 2, plus 1 minus 4 over e. Well, that happens to be a negative. And then if I test it at 3, I'm going to come up here, f prime of 3 equals 2 over e, natural log of 3, plus 1 minus 4 over e. That happens to be positive. So that means we're going from a negative slope to a positive slope. So that means this is a minimum. All right, now it says use your values of a and b and find out if it has inflection points. So we take our first derivative, which equals 2 over e, natural log of x, plus 2 over e minus 4 over e. These are just constants, which will drop out when we take the derivative. F double prime of x is going to be 2 over e times 1 over x, which is the natural log of x. These two go away. So this is 2 over e times x. Guess what? There is no x value that will make that 0. So no inflection points. Alright, moving on. Consider this function. Determine all the max and min. So I like to look at these. I'm going to take g prime of x. I'm going to write it like this, x over 1, and this thing I'm going to move down because that's what the negative exponent does for me. Right? So if I set this equal to 0, notice this term in the bottom, never 0, always negative. Right? E to the x is always positive, but since this is negative, that's always negative. So to find the critical point, I just have to worry about the numerator. So x equals 1 is our only critical point. So what I'm going to do is, I guess I can look at my second derivative, huh? If I look at my second derivative at 1, I'll write this x minus 2, and this will go into the bottom as e to the x. So notice this is always positive, right? I put a 1 in here, that means this thing is negative. If it's negative, that means concave down. So x equals 1 is a max. Alright? Alright, number 5. A rectangle has one side of 8. How fast is the diagonal changing at the instant when the other side is 6? So we're going to call this y equals 8, we'll call x equals 6, and they're telling us that dx dt, the rate it's changing, is 3 centimeters per minute. Alright? This y is not changing. They're not telling us it is, so dy dt equals 0. What they want to know is the diagonal, dd dt. What we do know if we use the Pythagorean theorem is that d is 10. So, if we take the equation that the diagonal squared equals x squared plus y squared, let's differentiate with respect to t. So this is 2d dd dt equals 2x dx dt plus 2y dy dt. Now we said up here dy dt is 0, so this term will drop out. So dd dt equals this thing here divided by 2d. So let's plug in what we know. 2 times x, which is 6, dx dt, which is 3 centimeters per minute, divided by 2 times the diagonal, gives us 1.8 centimeters per minute. So the diagonal changing with respect to time is 1.8 centimeters per minute. Right, this one isn't too bad. And it's okay if we work with d squared, the distance squared, as opposed to trying to take trying to do this and differentiating. We don't need to worry about that. We can differentiate like this, d squared, because we know d, we use the Pythagorean theorem, and we're looking for how quickly d is changing with respect to time. Alright, so that's the end of test 1, sample 1 I should say, and I'll work on sample 2 tomorrow.